So here are a few, my email address, GitHub link, LinkedIn. If you want to look me up, I will also make the slides available. So who am I? I work for 3 companies at the moment. Geosignum, which is a lidar data processing company, and we're building a web platform where you can watch and manipulate your lidar data sets. I will show a screenshot in a moment. I work for Athena Studies, helping them with development. They had some issues, so they called me over, and we're doing e-commerce and CRM there for essentially crash courses for university. And I work for Cirrus Nexus, which is an online trading platform for the food industry. Then there's one of the side projects I've been doing lately, which is at my university, where I'm, by the way, also studying computer science. And there I'm one of the primary programmers of the DevHub platform, which is an internal Git, SCM, continuous integration kind of platform. It's very similar to what GitHub, GitLab, Travis, Jenkins provide, but it's all in a box, and it's a solution completely tailored to the university environment. So we have the notion of assignments, groups, students, and that sort of things. And all that together gives me about 4 years of full stack development experience, primarily in AngularJS and some J2EE stuff. So I also promised the screenshot. So this is what the pointer platform looks like. You can't really see it with the lighting. Yeah, Karsten remembers it. So this is supposed to be the data set. We're looking at the street here. We see the cars, and this is actually what was captured by the sensor. And what we're doing is feature extractions on that and making that visible in the browser. Then this is DevHub. So pretty much looks like a regular SCM platform, or DevHub, actually. Cirrus Nexus, just showing the product availability on the map. And then lastly, the portal that we're building for Athena Studies, just a sneak peek. So it shows a few courses we're planning and their prices. And this is actually how this application works. And we will go back, we go a little bit more into detail as far as this application is concerned. One thing that you can already see here is we're doing university crash courses. And the way our company works is everything is always in a university or in a faculty or in a course of a faculty. And we see here that we're in the University of Amsterdam and the Faculty of Rights, I believe. So in this talk, what are we going to talk about? The topic is polyglot persistent object mapping. I'm going to give you a quick recap on polyglot persistent for those who don't know what it is or how it works. Then I'm going to sketch our use case, go into a bit into details there, how we map the domain, and then lightning strikes, we see what happened, and how we handled that situation. So polyglot persistence is about using different sorts of databases to store your data. And I got this quote from Martin Fowler. He wrote this back in 2011. And he mentioned the relational option might be the right one, but you should seriously look at alternatives. One of the interesting consequences of this is that we're gearing up for a shift to polyglot persistence, where any decent-sized enterprise will have a variety of different data storage technologies for different kinds of data. And we're already seeing that, of course. There are still a lot of relational databases out there, but as we've seen in the previous talk, there is almost no enterprise company that is not doing anything with big data or something similar. I won't talk about big data. I won't talk about analytics and time series either, but at least I'm going to show a few of the other approaches. So we will go through key value, document, and relational database. And then actually with the article mentioned here, there was this diagram. And I'm not sure if you can read it, but it mentions storing user sessions in Redis, financial data in RDBMS, shopping cart data in Riak, recommendation in Neo4j, which is a graph database, product catalog in MongoDB, reporting, relational, analytics, Cassandra, and user activity logs in Cassandra as well. So what database do you pick, and what characteristics are you looking for? So, of course, you first need to know what kind of data you're trying to store. The entire idea of polyglot persistence is using the right database for your kind of data. So you have to think of the size of your data. Does it even fit in one server? Because your relational database essentially stops working if it doesn't fit on one node anymore. You have to think about data integrity. Do we have a need for constraints? Do we have a need for transactions? Do we have a need for locking mechanisms? These problems or these tools that you may need are very difficult to achieve in a truly distributed system. So usually you do some compromises there. And you can also, for example, think of locking. If an object has copies around your entire cluster, locking essentially means you have to lock the entire cluster, which is luckily almost impossible. You have to think of types of access. Is the data immutable? And if it's mutable, do you have mostly writes, mostly reads? How does it work? And of course, you need to know, how am I going to use this data? What are the relationships? Do they have to be joined? Is there recursive traversal? Do we have some kind of prototypal inheritance or some sort of deep nesting? And that also depends on what tool you may want to pick. So the trade-offs for query and traversal. Well, most databases have quite fast access by ID. So if you just make it your primary key, you can, well, give me the first user, you will get it. The difference in key value databases is, though, that you can also distribute by the key, and by that means have a very easy and simple solution to create a distributed database really fast, complete with failover and redundancy built in. But fetching by ID is usually fine in any database. The nested structures, especially performant in document storage. Who knows the difference between key value and document storage? No one dares to speak? Well, it's a very subtle difference. Key value is really just stupid key, here's the key, give me the value. Document has a little bit more understanding of what's actually within the value, so it allows you to filter by it to query or select something in the value. Then, of course, there's the list and traverse through just all the rows in your table, which can be problematic in very large data sets or distributed data sets, because if your rows are spread across the entire cluster, you have to fetch the results from literally everywhere. Do you have to join relational data? Well, this is actually the point where the traditional relational databases excel. The recursive traversal is, of course, the selling point for graph databases, which are usually key value under the hood. Then we have some very special cases for querying, which are the text search, for which you usually use Lucene indexes. They're either implemented in your database or you use some sort of middleware. I think it doesn't really have to matter so much for your database choice, but it's something to keep in mind. And you have the spatial searches, for which there are spatial indexes. And then the one that's falling off at the bottom is comparisons, for which we have the all-known B3 indexes. So looking at the example Martin gave with the, I think, the 6 options in the diagram, let's quickly go through them. So he proposed to store user sessions in Redis. Who thinks that is a good idea, and why it's better than to store it in another database than Redis, or what makes a difference here? Yeah, persistence, but
For longer time.
for longer time.
Key values.
Yeah, Redis is key value, and I think primarily for Redis, it's just stupid key value. You don't really care if a session gets lost, but you just want to fetch it fast. And another selling point of Redis is that it has a notion of time to live. So you can just say, okay, this session needs to be there for 2 days, and then it should be gone. So very simple. Don't make it much more complicated than it is to store the user sessions. Then for the product catalog, it suggests MongoDB. This is, by the way, purely hypothetical. He doesn't really describe an actual system, but he's just saying, okay, MongoDB could be an option for this. Any ideas why? So MongoDB is a document storage, I believe. So
One request, you have everything.
yes, that's really the benefit. One query, you get all the nested data of one product. So, and if that product has some special properties, such as a bike having the wheel size, for example, whereas the CDs you're also selling don't have this, then you can easily extend the document with all sorts of properties to make that possible. Financial reporting, RDBMS, well, you want the most possible data integrity that you can have there. So that makes sense. Shopping cart React, I'm actually not sure why, but React is a KV storage. So it's probably also because you're never going to select all shopping carts. You just want, give me this shopping basket of this user and give it now. So that's also really stupid access. Analytics logs in Cassandra, I think primarily because it has insertion time ordering. So you can quickly say, give me the latest 10 or give me the first 10. And recommendations, a graph database, and then they picked Neo4j. So that's how we fill in this list of why one could choose to use different databases to get the job done here. So that was the quick recap on polyglot persistence. And now we're going to the use case. So our use case was as follows. We want to use a graph database as a primary store for our e-commerce CRM platform. And this is, by the way, the Athena studies case. So the last screenshot I showed you. And we want to have a recursive structure of clusters in which courses are given and sold, for which we want to measure the marketing convergence. How well is a university doing? Do we need to do more marketing in another city? What is the cluster performance? Do we get good feedback there? What is the revenue in a specific cluster? Or don't we get so many people in those courses? And we want from that compute the revenue and bonus for partners and business developers for that particular cluster. So I'm not going through the entire domain, but for showing how the object mapping would work using the graph database, I have a few entities to play with. So we start with a client object, or class actually. We have orders and we have payments, and they are linked with these connections, which in a relational database would typically be the foreign key or a joint table, and the entities being their own entities. So these are the classes that we're going to use for the talk. Now, in graph databases, it's not uncommon that you use Gremlin to traverse the graph. Who's familiar with Gremlin? No one? OK, cool. So what Gremlin essentially does, it describes how to get from one point in the graph to another point. So what we're essentially saying, start at the client, take the out edge as ordered, and take the in vertex from that, so we're at the order, and we name it orders. And then we take the out edge order transaction, and we take the in vertex of that as well, so you get to the payment. Then we filter the payments. Their state should not be null and should have that magical value of 100, probably something our payment provider decided. Then we go back to the order, and then we list those order vertices. And by the way, I didn't mention it, but this is the method to get the successful orders of one client. So yeah, what we are essentially doing, starting at the client, traversing to the orders, filtering by their payments. So who has some criticism for this piece of code?
There's no index.
There is, yeah, well, it could be under the hood, but even if there is, the only index that you're probably using here is defined by ID. So give me the client, give me the order, give me the... So yes, there's not really an index. What do we, oh, sorry, yes? Oh.
Massive chaining of methods.
Yeah, it's massive chaining.
Sorry, I wasn't quite clear. Gremlin, is this like an idea what you're trying to implement in a particular language, or is this?
Well, Gremlin, Gremlin is different than Cypher, yes. Gremlin is essentially a graph traversal library, and it's not database specific, so you can use it for Neo4j, you can use it for OrientDB, you can use it for almost any graph database out there, and you can use it both on the server side and on the client side. But it's primarily a description how to traverse the graph.
Okay.
And then it actually performs it under the hood as well.
Java.
This is Java. I think Gremlin 2 was intended to be used with Groovy, making the lambdas a little bit easier. But it's Java, yes. Anyone has something to say about these string values here?
Yeah, they are hard-coded, so if order transaction is changed, then it don't work anymore.
Yeah. Yeah, it's completely hard-coded. It's very aware of how the data is stored, how it's in the database. So if you make the smallest change to your schema, it already breaks, and there's no way to know. So what do we, I wrote down some criticism I had myself. It's very tightly coupled with the graph representation, lots of hardly maintainable magic strings. We don't know if this client incoming vertex was actually a client. It could have been an employee, or it could have been an order even, we don't know. It takes any input that is a vertex. And the same actually counts for the output. We just assume that this list vertex is a list of orders, but we're not sure. Yeah, we assume the schema is right and that it gives us a list of order vertices, but it could be anything. We also don't know the multiplicity. Does every order have only one payment? Can there be multiple? Well, of course, no one is going to pay twice, but what happens if a payment fails? From just reading this piece of code, you're clueless. And then we also have what if a transaction does not exist if the customer didn't have anything to pay. So if the order was €0, they probably don't pay anything, and this check fails, so the order won't get listed. So there's even a bug in it. And even worse, if we fix that bug in the domain model, as addressed, then the query fails because we changed the schema. So this is great. So the goal that we have is take away all the mental strain that developers face when they try just to get from a client, to orders. And this can be achieved through the means of consistency, type safety, schema, autocomplete, and also sticking to the law of Demeter. And what we essentially saw in this diagram or in this query, is the order doesn't know itself whether it was successful. So in order to know if the payment was actually paid, we have to get to the transactions and then see. So that's actually a modeling fault, maybe even. You just want to know, hey, was this order successful? I don't care that you have transactions attached. As a programmer, I mean. So under the hood, that's probably still what's going to happen. So we're breaking the law of Demeter there, and we immediately see how it could be useful if we have some sort of abstraction of order that just has a method that returns a Boolean. Yes, I'm paid. It's fine. So that was our use case. Now let's see how we can map it to a domain, actually. So in Java, there are a few persistence libraries. Who has ever worked with JPA, the Java persistence library? Hibernate, Eclipse Link, OpenGPA. Well, GPA is the most notable implementations. I just mentioned them, and it maps to RDBMS stores. So just relational data. It's also very tightly connected actually to relational databases. There's an alternative to it that's even older, strange enough, and that's called GDO, which is data store agnostic, and the reference implementation is data nucleus. I'm not sure if anyone has ever worked with that. Apparently not, and it has support for a bunch more databases. So Neo4j, MongoDB, Cassandra, HBase. Essentially, they do some sort of KV graph storage. Then there is also Hibernate OGM, which is actually Hibernate's NoSQL version of Hibernate. So you can use that with primarily Neo4j, but also MongoDB, InfiniSpan, and EHCache. Never heard about it. And you're experimenting supporting Redis, Memcached. No, Redis, CouchDB, and Cassandra as well. And then, of course, there are some vendor-specific ones as well. So, for example, Neo4j has their own Neo4j OGM. But probably, if you're abstracting your data library away anyway, you probably want something that allows you to switch between database implementations. So there are a few options to pick. So what does this OGM give us? And I'm just going to assume this to be a very generic object relational mapper. The annotations here presented come from the OGM from Hibernate, so Hibernate OGM. So I'm not sure if everyone can read it, but I basically described the three entities we just discussed. We have the client, the order, and the transaction. I only annotated the fields. You just have to assume getters and setters also being there. So if we have a list of orders, that means we can do get orders, set orders. We can add an order. And the same for client and transactions. So what we were trying to implement is some method get successful orders. And instead of just creating some sort of method that just lives somewhere magically and takes a client, I'm now putting it exactly in the client entity. And I just say, OK, this class has a method get successful orders. And that takes the orders, makes a stream from it, which is Java 8 Stream API, filters the stream by successful orders, and collects that as a list. And then, OK, where is the successful check? Well, that's in the order itself, which maps through, this should actually mention transactions. It's a typo in my slide. And it filters the transactions by successful ones, and then the successful check there looks if the status has the proper value. Any questions about this mapping?
What does OGM stand for again?
Well, I actually tried to look it up, and I'm not sure, because some people use it for object graph mapping, but Hibernate OGM also maps to key value storage and document storage. So actually, I'm not sure if it stands for object graph mapping, but they just needed something different than object relational mapping because they try to be NoSQL, and they needed another ladder to put in. I think that's the only reason that's OGM. But And in this slide, I fixed the bug, actually. So now we check if the total amount is 0, then it's also successful. That's the little bug we discussed. So say we have fetched a client entity from our database, and we call this getSuccessfulOrders method. How many queries do we run? Yeah, you can't get the exact number, but I'm just wondering if we can get an idea of how this would perform under the hood. So let's start with the order stream, which under the hood fetches all the orders of the client. So that would be one query to just fetch the orders. And then from the orders, we get to the transactions, which is also a one-to-many relationship. So depending on the amount of orders that you have for every order, you do one more query to fetch its transactions as well. Hibernate can actually optimize this by doing a join and fetching all the transactions immediately with an order, but it only works for one level of one-to-many relationships. If you start combining all this, then it comes down to n+1 queries, which can be intensive, but for this case it works. But by the way, that also happened in the Gremlin pipeline. So if the Gremlin pipeline figured out, hey, I'm now at this order, I need to get to the transactions, it would do a round trip to the database. Hey, do you have any more transactions for me? I'm looking for this order. So actually OGM is not the bad thing here, but it just makes it a little bit more clear that that's been done under the hood. So if we start using object relational mapping or object graph mapping, because we think it makes our code more readable, more easy to understand, because we can adhere more to our domain-driven development if we wish so, then we need a mechanism to transform our schema that we have to our domain, and there are some restrictions there. And as a general advice, I would say use concepts that are available both in your database and in your programming languages used. And in Java, that means no multiple inheritance, which is probably a good thing. And you use classes as first-class citizens. So in some graph databases, you can actually use, you can have properties on edges, which is probably like some sort of property on a foreign key in a relational model. It doesn't really work in object-oriented languages or relational databases. But there it's possible, and you should probably not use it if you wish to do this. I'm not exactly sure why this slide is here, but one of the pitfalls is we're really trying to use the best database for what it's good at. And one of the things we've seen at the Athena studies case is I mentioned we wanted to use a graph database as our primary data store. And in fact, as our only data store. And this is usually a bad thing, because our goal was, to use the best for our specific purpose. If you start doing that, there are some implications, because now you all of a sudden have 2 databases, or even 3 databases, or 4 databases to handle and maintain, to implement this ORM for. But this is a huge task to figure out how the backups work, how you set up load balancing, failover. So in the startup, be ready to spend some fun nights on doing that. And in enterprise, get some DataStax support or somewhere else. Be ready to send your ups for a few days of training. And, and then still the knowledge is necessary. So don't underestimate the effort that goes into operating all these databases. And that's also the point where you have to ask yourself, what will actually be the added value for the business? And if you don't have this time, your safest bet is probably just a relational database. So now we get closer to the storm already. Always measure the performance of your database for your use case. Because one day you may find yourself running with your nice little database product, and all seems nice, and your database slowly fills up with new data as customers start to use it and start to like it. And then all of a sudden you see your API endpoint times, your response time increase. And at 500 milliseconds, you think, oh, I'm still good. It's not going to grow extremely more. And then all of a sudden, it takes 1 second. Then it takes 2 seconds. And then in 2 weeks, you're at 20 seconds, and you hit the timeout of your browsers. And people already got really frustrated that your app is not working. And then you're in big trouble. And this is actually what happened to us. That the database we chose was not the right database. It was not Neo4j, it was another database. And we picked the wrong one. Or at least we didn't know. So we started seeing these times and we were thinking, are we under attack? Where do all these times come from? Why is everything so slow all of a sudden? We started profiling our own application, doing a lot of debugging. Of course, we gained a bit of performance. You always find something if you put your program under a profiler. But we didn't just quite get it, and then we started to get suspicious about the database. And that actually turned out to be the problem, because the profiler actually on a quite small result set showed a lot of use in the string constructor. So it was doing a lot of string concatenations, and even on returning somewhere between 10,000 and 100,000 rows, the database would crash with an out-of-memory error, which is a shame for a database. So time to reconsider, what can we learn? Our specific database had some serious bugs, issues. They themselves tried to they mentioned it to be design faults or something. Even though we had a few recursive queries, our domain model was mostly relational. So if we look at the client order payment example, that doesn't benefit at all from being in a graph database. It can be represented in tables as well. And we made some severe compromises to our data integrity in order to use this graph database. We had no foreign key constraints. We had no unique constraints. And we needed a solution quick, because we had about a month before we would get a lot of traffic in the new year. So what do? Can you do a rewrite in a month? Usually when we think it's possible, it turns out to take 2 years or so. So lightning strikes. So my emergency plan, and that's actually what we turned out to do, is let's go back to relational. Because whatever we do in a month, we're not going to find the time to research new databases, to learn about their characteristics, to transform our model to them, to the new database. And we're not having so much benefits from using a graph database anyway. But I knew that we should stick to the same API and the exact same data model. Because otherwise, you're not replacing your data store layer, but you're actually replacing your entire application, which has a lot more risk of breaking things. It's just so much more, you don't really know how much time it's going to take then. And I really wanted to have this done in 2 weeks, actually. So back to Postgres it is. And then you need some tools. Because, well, we decided not to use Postgres for a reason, but now we suddenly have to transform our schema to Postgres. And we were actually using all these fancy key value stuff, so nested fields, nested columns, nested stuff. So we at least wanted some consistency there. So what you can do is denormalize using embeddables. And what this essentially does, if you have multiple entities that all take an address, maybe a company location and an employee as well or something, then you can make this little class being an address, and you can include it in your employee or in your company or wherever you want to use it. And it will actually be included in that table, but it will have consistent data types, consistent column names, consistent validation, and you're using the same getters and setters all the time. So that makes it at least more recognizable to the developer, because you're just thinking, okay, I have a client, how do I get to the address or to the street? Okay, just client get address, get street, bum. No vertices, no edges. Very simple. Another thing you can do if loading is an issue and you don't want to fetch from other tables as well, just use a JSON field. It feels kind of an anti-pattern, but it's kind of weird that we call it an anti-pattern in RDBMS if it's actually a good practice in key value storages. So why not? Just store it as a JSON value. And there's actually some Hibernate extension that makes this possible. You can ignore this annotation, it's unnecessary. But you just define a custom type that maps to a JSON column. And Postgres has a native type for JSON, so you can also query it. But if your database doesn't have a JSON type, just use a text field or a long var. And then we had, how much time do I have, actually? Enough? Okay. Then we had to get rid of the recursive entities. Or well, I mentioned that we wanted to keep using the same domain model. So actually, we must stick to our recursive entities. So we defined our recursive entities. Well, how do you do that in Hibernate? You name your entity, recursive entity, you give it a parent that points to another recursive entity, and then you make a set of its children, which is mapped by the parent. So what you can do, fetch one recursive entity, get children, get 0, then get the children of that one, for example. But how do we query this? How do we do a recursive query that we would do in Cypher or that we would do in Gremlin? Well, Hibernate can't because it's not optimized for recursive functions. And accessing these ones costs you a query. So if you start at one recursive entities, then get to that children, get to the children of those, get to the children of those, it starts to get really expensive in terms of the amount of queries you're running. So we had to do something smart there. Well, there are some SQL anti-patterns. I copied this from a book, so, but I have the book here as well. So if you want to have a quick look at it, I have it with me. And this is not about recursive entities, but this is about comments, and you can place comments on comments, essentially. And the comments that we're trying to select here are listed here, and the arrows indicate that, that a comment is made on another comment. So if we want to select all, well, naively, you just start joining them all together in order to get all the comments that you're looking for. But you need one join for every level. So this is the select star from. This is the first join. This is the second join. This is the fourth join. And if someone comments on this one, it won't be in the result set. So unless you want to restrict the depth of your tree, this query is not going to work. Well, then there's another anti-pattern that you can use, which is actually very common in practice, and that is to just with every node in this tree, store its path, and then do a like expression, where you just say, okay, I want all the comments that start with 1/, and then that gives you all the recursive children of 1. Any questions about this query? Let's move on to the next slide. And this is actually what you can do if your database supports recursive queries. So how it essentially works is you define a recursive part that exists of a base part, which is select the first comment. Then you have the recursive part, which essentially says, okay, in this part, I'm going to select the children of the last result set and amend that to the result. Then we get some temporary table called comment tree, and we can select star from that, and it will give us all the comments recursively. Of course, while a lot of databases are now starting to have these recursive queries, I think Oracle has them, Postgres has them, H2 has them, MySQL I'm not sure. But under the hood, this still functions as joins, and it's actually quite computational intensive. So on the database side, this is not really as ideal as a graph database, but the real benefit here is we have only one database round trip. So we have only one query to send to the database server. We will get our result, even though it took a while to compute it, maybe 100, 200 milliseconds. But we only have to do one query, as opposed to having to do individual queries in the other case, which then all have their own round trip times. So how do we do these recursive queries in Hibernate? Because you can do native queries, but they don't really map so well to entities, especially if your entities are complex. There have been 2 papers, research papers, quite recent also, published by Anita Sumowska, something like that. Some, I think, Polish university started researching, can we make these recursive queries? Can we implement them in Hibernate? So I was really happy when I found this, and I'm really sad that they didn't open source anything of it. So it's just a paper, just a proof of concept, just showing, hey, we can do this. We show you some nice statistics. We gained so much performance, and then no code. Sad, but that's our life. But luckily, I found this little framework here, BlazeBit. And BlazeBit is a company from Austria. And they have this little extension called Blaze Persistence. And they make these recursive queries available in Hibernate. And what you essentially do is you create a CTE entity, which is needed to store the temporary table in that we mentioned earlier. Then you create this criteria builder. This is the base case of the recursive part, and this is the recursive part of the recursive query. If you have this entity and this criteria builder, then you end up with this query. It's quite complicated, but I will make the slides available so you can have a look at the query and kind of see what it's doing. What it's supposed to be doing is recursively fetch the levels, the nodes in the tree or the comments, and with every comment, list the level of depth in the tree. So that was actually my talk. Are there any questions? Karsten?
So what was the performance gain in the end? Because performance cost, I mean, in the beginning it worked fine.
Well, why the solution turned out to be not effective? Or well, primarily the problem with Gremlin is that every step is computed in the client side. So if you do a traversal, you're essentially fetching all the entities you touch. So if you touch in your traversal 10,000 entities, you're fetching 10,000 entities. And well, even though it's still possible to fetch 10,000 entities, you don't fetch them in a batch. You actually just keep asking, hey, do you have this for me? Hey, do you have this for me? And with every step you have this network round trip. Well, if it's localhost, then it's 2 milliseconds. But if it's another node in your server, then it's like 5 milliseconds for every request. If you do that 10,000 times, your performance is gone. Then the lucky part is you can also do this Gremlin pipeline on the server. And a lot of graph databases also have their own native SQL language, which you can use to do the same. And then you can express this logic in the server, create the result set there, and only push the result set to your application. So that would be a feasible approach for us. But we had two other problems. And one problem was that the database we picked was just too slow and too bad. So even if we did that optimization, it would still be too slow, and we would outgrow our database in 1 of 2 years of usage. And the second problem is because we knew it wasn't a durable database anyway, we didn't want to invest time in implementing native queries that we would have to recreate if we started to transition to another database.
I was in the beginning. You showed different database systems for different types
Yeah.
of data, and for example, user data. Redis. Or something?
Yeah, I think they chose Redis. It can really be anything. Just quickly getting the. Yeah, so there it is.
Redis? Yeah. And now, for example, MongoDB or even as a relational database. I was wondering, I suppose that in Redis you have user information, which are users, what are their credentials, and what is their time to live, how long is the session. But suppose you want to extend functionality to add certain features only to specific users. For example, only some users may see financial data and others not. But then you have chosen a database like Redis to store, which does nothing about financial data.
Yeah, but in your
have you then made a bad choice and have to change to a relational database?
No. I'm not saying that you always have to. Not at all. I still think that our initial idea of using a graph database for some of the computations we've been doing was actually a good decision. But the problem was it wasn't a good decision for all. For example, we also did the financial reporting in that database, and we lost some orders. They're nowhere anymore. And so it was more a bad decision to do everything in a graph database. Mm-hmm. And the only reason that we said, okay, we're not going to transition to a decent graph database or to set up another database next to it, but decided to do the weird step to go back to relational was only because we had extremely little time, and we just wanted to use the known way. So we were sure that we knew the performance characteristics, we knew it would work, we knew we had all the tools for making it highly performant, to make it distributed, to have failover. So that was the primary reason. So I still think that this entire picture can still be beneficial, but you have to be aware that if you do this, you have 6 databases to maintain. You have 6 databases to learn about. You have 6 databases to wire up in your application. And that's just a lot of work. So it only gets interesting at a certain scale.
Yeah.
Does that answer your question? Or?
Yes.
What database and server were you using?
Well then my talk kind of transitions to a flame on that database. So I'm only going to tell it in private.
Were you doing any user verification? Were you how were you verifying the users? Do you have
That they have the proper permission, or?
Yeah.
Yeah, we do that at application level. So if you're as far as getting a connection to the database, you're allowed to see everything.
Okay. And then what do you do? Are you hashing the values? What are you doing?
For the keys or for what?
Yeah, for the user passwords for their.
User passwords are bcrypted, if you know what that is. Bcrypted, so salted and hashed.
Okay.
For example, the shopping carts, they have both an internal identifier and an external identifier. The internal identifier is just incremental, shopping basket 1, 2, 3, 4, 5. And the one that goes to the customer is actually an encrypted token that gives you access to the shopping basket, because otherwise you could just start incrementing IDs in your browser and you would get someone else's shopping basket, which can lead to funny situations, but it's not really useful. But does that answer your question?
Yeah. I was just saying, what hashing algorithm are you using?
Yeah, so for passwords, bcrypt. For the token generation, we use JWT, and I'm actually not sure what hashing they use, but it's like a key generation with a private key part, and you put some values in it and it creates a key. And for some other hashing we use, I think, SHA-512 or something. That were the questions? All right.